All right. Where are the humans? No, I guess it doesn't really matter. All right. Jack is in. Let's just watch me watch someone else play Hearthstone. It's all my recommended channels on Twitch. Sounds fun to me. Alright. We have half of our people. There's Riley. Very exciting. I mean, it's a viewer-friendly game. I don't know if exciting is the right word, but yeah. Yeah, that's... I like it. It's a good meme. Alright. Is anyone on Twitch but not on Discord right now? Because I would like to start class. That sounds fun to me. Give it like start. Alright. We're only missing Devin. He'll survive. Okay. So last time we left off with like the epsilon-delta definition of continuity, right? And we still need to prove that that is equivalent to our open set definition. So this is 186, right? So we have two different definitions. And so f from x to y, I'll just write them both out here, right? So it's continuous at a if for any positive epsilon there exists a positive delta, such that, and the way I'm going to write this actually is the way I want to do it in the proof. I want to think about this in a more generalizable way. So I'm going to say such that if x is in the delta ball around a, right, this is exactly a minus delta to a plus delta, right? So it's just saying it's less than delta distance from a, then f of x, these are very specific here. In this case, this is r. Then f of x is in the epsilon ball around f of a, right? So this is just, trying to kind of use our terms, and especially when we talk about like general metric spaces or, Euclidean spaces of dimension higher than 1, like this still works. You just take the ball instead of saying, the interval. I mean, the absolute value wouldn't make the same sense, but it's just like distance less than. Okay? And then, so this is our definition 1, and then definition 2. So that's continuous at A. So if it's continuous, then this would be true for any A, right? And then we say f from R to R is also continuous if f inverse of u is open for any open u in R. And by 185, it suffices to look at basis elements. And so we can say u is really just like some open interval. Right. Okay. So let's try to start proving this. So the idea here, which way do I want to do first? Okay. So we'll do, say, 1 implies 2. Okay. So I'm going to start with you know, some interval AB, and I want to show that its pre-image is open. And I'll probably usually not do the double parentheses there, and just, you know, it's a pain to write every time. So I think it helps to draw a picture here. So basically I'm going to think of this as my target space down here. So I've got some AB, and then what I'm going to do is show that this guy is equal to its interior, right? So I know the interior is always contained in it. So basically I just need to show that F inverse of AB is contained in its interior. If I show that, then it's open, right? So, okay, this maps back up. So take some y in the pre-image. Well, that means that f of y lies in here somewhere, right? And so the idea, right, I have my epsilon delta definition is this 191. This is 186. 186, because we didn't quite finish the things assigned last time. And this wasn't assigned. This is something I just need to, well, you guys probably could have figured it out, but I just wanted to prove this one, I guess. So y is in here, so this means f of y is in here, but we have our epsilon delta thing. So what this means is, for any epsilon ball around f of y, I can find some corresponding interval up here, right? So who knows what f inverse looks like, but basically, right, you know, maybe my f inverse is all the way out here. The point is, I can find a corresponding delta ball. So this is little epsilon, epsilon. This will be a delta and a delta corresponding to it, such that this guy just maps into here, right? This is what my epsilon delta definition tells me. And I can choose any epsilon, right? It's true for any epsilon. So I'm just choosing one such that it still lies inside the interval from A to B. So this means, right, that f of y is in the open interval from A to B. Okay? Then there exists an epsilon greater than 0 such that the epsilon ball around f of y is contained in AB. That's just this picture. My epsilon ball around it is contained in my open interval. Okay. Then, by epsilon delta continuity, there exists a delta greater than 0 such that my delta ball around y is going to be contained in the pre-image. So y, again, it's because what this really means, right, is if the distance between x and y is less than delta, then f of x is within epsilon of f of y, and so that means f of x would be in the interval AB, and hence x would be in the pre-image of AB. And so that's exactly why, you know, you're seeing that this whole delta ball is mapping inside AB, and so it lies inside the pre-image. How do we know there exists an epsilon ball? Because we're inside an open interval, so you can just choose the minimum distance to A or B from your f of y. Why do I call it a ball and not an interval? Because it's a more generalizable notation. I mean, the balls, right, like those are things that are defined for more than just R2. It's just things distance less than this away. It's just that, you know, they're different dimensions in different dimensions. It is an interval. I just don't want, like, yeah, I guess I could, it's the radius of the interval, but yeah. Devin, does that make sense as to why I know there exists one? Okay. Cool. And so, well, I now know this is an open interval, right? We know b delta of y is open, so y is in some open set inside the pre-image. So y is in an open inside the preimage, so y is in the interior. And thus, the preimage lies inside its own interior, and thus must be open. That was me justifying this. I mean, I kind of tried to make it clear from the picture, but if you wanted to see rigorously why something inside this delta ball around y lies inside the preimage, this is why. All right. So then we want 2 implies 1. So here, right, we know preimages of open are open. But here we're starting with some epsilon, right? We need to find a delta, or the existence of such a thing. So again, it helps me to draw a picture. So I have some, this would be true for any A, right? So you just pick some random A. So I've got some A up here, and then I have f of A down here. And then I choose my little epsilon ball around it, right? So let A be an R, and let epsilon be greater than 0. Okay. Well, the nice thing about this is already an open set, right? So then the epsilon ball around f of A is open. So f inverse of it is open, since f is continuous in the, preimage of open is open sense. But an open set, right, it need not be a basic open set. So we don't know we just have like an interval upstairs. It could be like a union of intervals. So maybe I'll just draw that. Like maybe I have something that looks like this. But the point is, right, like maybe this is my preimage. The point, however, is that A lies inside some basic open, right? So this open set, this is a union of open intervals, and A lies inside some open interval. Right, you have a union of basic opens as your open set. A lies in at least one of these basic opens. And so that's like this guy here. Now it may not be symmetric, but again, you can choose like the minimum distance or, halve the distance. It doesn't matter. The point is, right, you can find an a delta ball inside it, right? It may not be symmetric, but there exists a delta greater than 0 such that the delta ball around A is still inside the preimage of this epsilon ball around f of A. Does this statement make sense? So basically, I know there's an open thing upstairs containing A. I just find a nice little delta ball inside it, a nice symmetric interval inside. I can always do this because I have a gap, right? It's an open interval. And then the point is this still lies inside that preimage, right? It's still inside the black interval there. Well, what does it mean to be inside the preimage? Well, that means that when you hit the image, right, it's going to lie inside. So thus, f of b delta of A. Wait, what am I trying to show here? I just wanted to show that this lies in the interior again. Oh, no, I just needed a delta. Yeah. Right. This lies inside this guy, right? Just by definition of preimage. Thus, right, if your distance from x to a is less than delta, right, if you're in the delta ball, then, I don't want a ruler. What did I just hit? No, go away. Why? What did I hit? Alright, whatever. It's just going to be in the corner of the screen for the rest of the class, apparently. Then your distance from f of x to f of a has to be less than epsilon, because we end up, after doing f inside, we lie inside the epsilon ball. So epsilon-delta continuity holds. The ruler button is next to the colors. Oh! Yeah. I didn't see it there, because it's white and it blends in. Thank you. Devin, comment? I know this is a pain, but is there any chance you could write this up? I don't feel comfortable just reading through it. I want to study it a little. I mean, it is written up, right? Or what do you mean by that? Like, I post these. Okay. I was gonna say, I mean, I can make it like a little more formal, but if this suffices, then that'd be awesome for me. Yeah, I post all of the things in daily online notes on Canvas. I will admit it is a little weird because I don't have page breaks here, so there's some weird things. So let me know if it sucks, and then I can just like, I can do a better job. Okay, so this is great, right? And this actually works for any metric space. So again, like if you have some notion of distance, then you can really define continuity this way, and that's great. At least, you know, if you had seen this a lot in calculus, you'd probably feel better about this because you'd be like, oh, this is my familiar definition. But instead, maybe both of them feel a little foreign and it doesn't feel that great. But believe me, it's great. If you take analysis, it will feel great. So let's talk about 187. So this is, you know, one half of this is basically on the problem set where, I mean, it's not in the actual problem in the book, but I want you to think about all of these functions and why they're continuous in the epsilon delta way without just using this theorem as a hammer. And then the one that you had to do for the homework was show that it works for the preimage definition, right? So we had three functions. We had one which was just a simple translation, right, just shifting by 2. One was a scaling, and one is squaring. So we want to show that these are all continuous via the preimage definition. So how did you think about these? 2 of them are definitely pretty quick. Third one may requires a little bit of thought. But I would like to hear from you. So I want a little like Mario guy, like guy with the hammers. All right. Any thoughts? I mean, I looked at all these. You had everyone had 1 and 2, right? Mm-hmm. Mm-hmm. Yep. Someone else want to talk about G? G inverse of this is what? Yep. Cool. And then I saw some dangerous things on this one. What is my pre-image here? No, we don't have to be worried about negative numbers because you're taking, okay, so maybe. So, yeah, the image is only non-negatives, you're right. So what is H inverse of X for a negative number? Let's look at the graph. Yeah, so that gets at the crux of if they're both non-negative. Doesn't answer this question. So are you saying empty set? Right? There are no things that map to negative numbers. No, you don't. Because if A... No, because of what Nick said. So you get this if A is greater than or equal to 0. Right, because what you're saying, Devin, is look at the red thing on the y-axis. You're saying, like, have a half-open thing going from here. What is its pre-image? It's going to be all the things from here, or maybe I'll do it in a different color. It'd be all the things from, like, what? Undo. All the things here to here would end up lying in this, or, okay, actually, back out here. And then I trace this over, and I get, yeah, here. So, like, this would be your pre-image of that vertical open set. Right. 0, I mean, 0 maps to 0, but then, like, anything above it, you go left and right, and they map to it, right? So, like, H inverse of 0 to 2, or, sorry, let's do, yeah, negative 1 to 1, right? So H inverse of negative 1 to 1, they're all the things that square to things between negative 1 and 1. That is negative 1 to 1, because anything if x is in -1 to 1, x squared is in, well, 0 to 1, but that's fine because the preimage of anything between, 0 to 1, which is a subset of this. And it is equal to the preimage because anything to the left has empty preimage. Right, yeah. Yeah, because H inverse of -1 to 1, right, it's a union, so it's like H inverse of 0 to 1 union H inverse of -1 to 0. But this guy is just the empty set. So it's just like -1 to 1 union empty set. Right, negatives don't add anything when you take preimage. That's not an open set. Or do you mean including or not including 0? So I mean H inverse of 0, 1 is equal to -1 to 0 union 0, 1. Right? These are the things that square to things between 0 and 1. No. It doesn't include 0. It doesn't include 0 here. Almost the same, yeah. Right, because again, for the preimage, like all I'm looking at is, okay, what are my y values? And then I'm going, okay, what are the x values that get me there? And so basically, if you include 0, then you're just getting a connected open interval. If you don't include 0, then you get two disconnected intervals. Or, yeah, that you get two disconnected intervals. Yep. Sure. No, -1 to 1, because -1 squares to, like, -1 squares to 1, 1/2 squares to 1/4, like these things, you have to go both directions. Right? You're talking about what things on the x-axis will get you in the y-axis between here. That's all things travel over here, from here to here. Right? I square anything in here, I get in here on the y-axis. Yeah, the y direction, yeah. It very much depends on what your right bound is. Negatives, yeah, negatives don't add anything, right? Because like for the pre-image, right? I'm looking at like what x values give me my y value. If you choose any y value that's negative, well, there are no x values that give me this, right? My graph doesn't touch below 0. All right. So from looking at the assignment for today, seemed like this stuff was making sense for the stuff assigned today. And I mean, we can maybe talk more about this one after. I think looking at the graph and thinking about what maps to what helps. And again, just remember that like negative square to positives, that's important. So 188, the first one, if we have x with the same topology, right, is the identity continuous? Well, yes, right, because the pre-image of any open U is itself, right? So, so clearly still going to be open. Yeah. Yep. What about from R standard to R the lower limit? Well, you don't need it. You need it for a basic open, but you don't need it in general. But all you need are, you would need some open. Right. Yeah, but I mean that's not really the point. It's more just that like there exist some open sets. Like the pre-image of some opens are open, but like these specific ones are not, and like that's enough to disprove continuity. And again, by 185, we usually look at the basic opens anyway, and so that's yeah. Yes, wait, pre-image, yeah. Yeah, I mean, that was the comment I made on yours. You just switched your arguments. So I guess, Will, you know the answer to the next one then. So is this guy continuous? Looking at pre-images. Yeah, it is, right? Because, again, we have our basic opens. That is AB, but this guy is open in the lower limit, right? We've proven that before. Cool. Yep. So I think this is interesting, right? Like you very much care about the topology and not just the space. You know, it's somewhat similar to what we saw in group theory, where like yes, you can absolutely have bijections, but have spaces not be isomorphic because those bijections, you know, cannot be homomorphic. And this is kind of similar. Like identity is very bijective, right? But may not be continuous, and thus, you know, would not be a homeomorphism as we define that here soon, because the topologies we put on these sets are different. So the added structure kind of screws things up. Cool. Yeah, I saw some different ways of thinking about this one, so I thought this was kind of cool. So we've got the map to the finite complement topology on R, given by x minus 1 over 2. Does anyone want to talk about how they kind of thought of this one? Mm-hmm. Yep. Yeah. Yeah, exactly. Cool. Yeah. I saw some other routes which somewhat similar, right? That basically, if the complement is finite, so alternatively, alternate route, U complement is finite, and F inverse of x in general is 2x plus 1, so you only get one thing in the pre-image, right? For each point, then this implies that F inverse of U complement is also finite, and so F inverse of U is the open interval, just kind of the way that you showed, right? Is union of open intervals. I mean, it relies upon the same basic thing, that if you only remove finitely many points, then you have a bunch of open intervals that make up your space. And of course, it's very important here, right, that the preimage is like 1 point per, because in general, the preimage of a finite set need not be finite. We saw that with like the projection kind of thing, the quotient map, right, where we sent like all negatives to A, for instance. The preimage of A there is very infinite. Cool. Then number 2, yeah, I think everyone pretty much got this, right? It's essentially the same idea. It's kind of combining the previous problem and then this previous step. So we have the same map, but we're considering it from R to RL. And so here, if you have G inverse of a half open guy, you get 2a minus 1 to 2b, or sorry, 2a plus 1 to 2b plus 1, but this is half open, so not open in R. Cool. Okay, so 190, this is cool. This is actually the universal property that defines the discrete topology. So if X has the discrete topology, what did you guys say must be true? What can we say about F, any F, from X to Y? Nice. Yep. Exactly. Preimage is some subset of X. All the subsets are open, so any preimage of an open set must be open. Cool. Yeah, so basically another way I could have defined, if I started with continuous functions, and I never told you what the discrete topology was, I could define the discrete topology as exactly the set, or the topology, such that if you have a set, then it's the unique topology such that any map from this topology is continuous. So basically you could use 190.1 as the definition of the discrete topology, that any map out of it will be continuous, which is really cool. So it's the usual argument for universal properties, right? You would assume there's some other one, but there's only a unique map out of each of them, and you always have the so it would be from, in that case, right, they're both topologies on X, so you would have the identity map between them. Yeah. Yeah. So you could show they are homeomorphic if you have another one. So it is unique. Okay. So then, right, like a very natural question right after that, you're like, okay, every map out of the discrete topology is continuous. Well, and again, like 2 kind of gives you a bit of the other direction. Like, okay, if it's not discrete, can I still have it be true that all my maps are continuous? Like, is this really a property that is unique to the discrete topology? And the answer is yes, right? So if X does not have the discrete topology, can we come up with what is A? Oh, X. Okay. So what is your Y here? Oh, it's definitely not cheating. I think it's the way you pretty much have to do this, right? Since the original X has some, say, V not open in X, then, and so F is your identity map, right? So then V is open in Y equals X, since discrete topology. Let F be the identity, then the identity inverse of V is V. So identity is not continuous. Right. Open in X discrete, not open in X. And I think this is like really the only way you can like guarantee it, right? Because well, I mean, you may not know it is the, yeah, no, I mean, you can't really guarantee, right? Like if you have this V that's not open, like how do you know what topology has V open on the other side, right? Because I think you basically have to do X. Like I don't know what else you would map it to. I guess you could map it to some product including X, but basically it would rely on this argument. And then it basically has to be the identity map because you want something to map specifically to itself to compare the one it's open in and one it's not open in. And to ensure that it's open in the target space, you basically have to say it's discrete because that guarantees everything is open. Okay, we will come back to 191. I don't know how long that's going to take, so I wanted to talk through the things that we had assigned, and then I can prove some stuff from 191. It's just kind of lengthy just because it's 4 steps there. 192 seemed like most people felt super comfortable on. So, right, you have f from x to y and g from y to z. These guys are both continuous. Then g composed f from x to z is continuous. And yeah, everyone did this, right? You guys were just looking at the pre-images, right? And you know that the pre-image of g inverse f is equal to, or sorry, maybe I should say of a set of a u is equal to f inverse of g inverse of u. You know this guy is open in y since g is continuous, and thus you know this guy is open in x since f is continuous. Cool. And obviously u is a subset of z here. We are geniuses. Exactly. Okay. How about 193? This should be somewhat quick, right? So it probably suffices to just do one. So the projections, why are these guys continuous? What was 161? Was it? Oh, that it was the yeah. Okay, yeah. Yeah, and I mean the argument, right, is what is the preimage of some u that is a subset of x? Yep. And it's because you get this, right? And so this is the argument, but yeah, exercise 161 directly gives it to you as well. Cool. And that was the argument for 161. Nice. All right. So I think this was probably the most challenging one on the homework 194. The key is figuring out how to write one in terms of the other. Right, so here we have f from this, and f of z is given by its coordinate functions. Basically, we have different functions in each piece that tell us what happens in each coordinate. And the really nice result, right, is that f is continuous if and only if f1 and f2 are both continuous. And so that's something that we often like to do, right, is break it down into the coordinates, into smaller pieces, and deal with it there, and we can do that in this case. So why is this true? Stroke. It's fair. Yeah, I think it was a fairly challenging problem. Okay. Cross V is open. So here, let me just stop you really quick and give just to give a little guidance for like what we're trying to do, because yeah, I see where you're going here, I think. So the key, right, is we want some way to write f1 inverse, or sorry, f inverse in terms of f1 inverse and f2 inverse and vice versa, right? Because if we want to say that like f1 is continuous, you need f1 inverse of u is, well, somehow f inverse of some set, right? Because you want to use the fact that you know f is continuous. Or on the other hand, if f is continuous, you need to write it in terms of these guys' preimages, which are continuous. And so I think that's where you're going, Devin, in writing some relation between the preimage of f and the preimages of f1 and f2. All right, sorry, go ahead. Mm-hmm. Mm-hmm. Yeah. Yeah, and then okay. Okay, yeah. So right, and this really gives you both directions, pretty much, right? So I mean, if you want to go this way, so really this has nothing to do with our assumption up here, right? I haven't used the fact that f is continuous. This is just true always, right? This is just by definition. So if f is continuous, then if I want to show f1 inverse is continuous, for instance, well, f1 inverse of u is equal to f1 inverse of u intersect z, right? I intersect with the whole space, and I just get my thing back. And then, as Devin noted, or sorry, f1, f1 inverse of u intersects, well, how do I write it in terms of f2 inverse of v? Well, z is the preimage of y, the whole y, right? So this is f2 inverse of y, because anything in z maps to y under f2. And by our thing above, this is f inverse of u cross y. So this is open. So if f is continuous. Nope. Right, because right. So here, if you take the whole space, it doesn't matter. Right. Now, if you wanted to say like f2 inverse of some v is exactly the thing, yeah. There you wouldn't know that it necessarily maps onto some subset. Yeah. So if f is continuous, then f1 is continuous. So similar for f2, right? So like f2 inverse of v is equal to f inverse of x cross v. So that gives you... Oh, absolutely. Yeah. Yeah, that's why I didn't really write this one. And then going the other way, right, you have f inverse of a basic open, right? Again, all we need to consider a basic open, so u cross v is enough, is equal to this. But these are open by assumption, right, because they're both continuous, and intersection of opens is open. Finite. Yeah. Any questions on that one? I mean, the key was obviously like this observation, right? This was the key. Yeah. And if you didn't see like this, right, like this requires maybe a bit of a trick, but if you really boil it down and look like element-wise at this guy, right, like this is the set of z in z such that f1 of z is in u. And so notice, right, that like all I'm deciding is that my first coordinate must be in u, but I don't give a crap about the second coordinate, right? So like I don't care about f2 at all. And so basically that means that it can be anything, right? So like I could rewrite this as the f2 of z is in y, which is basically the same thing as saying nothing. And then that's another way to get this included. At which step, Rippy? Here? Oh, here. Yeah, okay, yeah. It is definitely an and, right? Because both are required. Yeah. Cool. Yeah, it's a nice proof. Just takes some fun little playing around. But again, the result is really nice, right? So now we have like coordinate functions and we have projections. So basically we have nice ways to think about like coming from a product or going to a product. And both of these are continuous, and so that's going to be really useful. What is that? Salt. Okay. Okay. Fine. Let's do 191. This is going to be terrible. Okay. So, what is the statement? Right. So we have these 4 equivalent things. So we're not going to always use all of these guys, but a few of them are nice, right? So like 3 especially is nice, that the pre-image of closed are closed, right? So that's makes sense if pre-images of open are open, that their complements, like pre-images of complements, work nicely, right? Also by that 27 that we did way long ago, right? So in general, F inverse of x minus u is F inverse of, or the pre-image of x minus the pre-image of u. This was in 27, so this is something that's kind of useful. But here, I mean, you can get that from continuity pretty quickly when you think of complements, but that would be like 1 implies 3 is easy. But this is maybe a little easier to actually go 1, 2, 3, 4, 1. 4 is also nice, so for any point that you have in your domain, and any open set containing its image, then you can come back and say that there's some open neighborhood around X that maps into, basically, I start with little x, inside my big X, I go to Y, I have f of x, I take some v, right? And basically what I am saying is there exists then some u around this guy such that all of u maps into here. So this would be like f of u. So basically, it kind of makes sense, right? This is the epsilon delta kind of picture you have, and this is really focused on one point at a time, and so this is what we would call being continuous at the point x. So this is useful in general as just like several different ways to think about continuity. I think the second one is a little weirder, right? That f of the closure belongs to the closure of the image. So the image of the closure belongs to the closure of the image. That feels less intuitive to me, but the other ones feel pretty intuitive, pretty natural, and so they do get some use, and so it's nice to have them. Just no. Okay, so let's do 1 implies 2. So we have f is continuous, and we want that f of the closure is contained in the closure of f of a. So really you just follow your nose here, right? So I want to show subset inclusion. So let y be in f of a bar. So this means y is f of x for some x in a bar in the closure. I want to use 79, right? Like I have a point in here, I can use 79. So I basically want for any open neighborhood v of f of x that v intersect f of a is non-empty, right? This is what I want. This would be using 79 to show that I'm in the closure of f of a, right? Because I intersect f of a non-trivially. So we just kind of break it down, right? So I've got my f of x. and x is in this. Okay, so take some open neighborhood v of f of x. Well, I know stuff about things in x, not y, right? And I'm in y right now. Well, how am I going to go back? I'm going to take the preimage, right? And f is continuous, so I know that the preimage of v is open. Then f inverse of v is open in x. And since f of x is in v, specifically we know that, x is in f inverse of v. So we have an open neighborhood of x. X is in the closure of A. What can we say? Well, if x is in the closure of A and this is an open neighborhood, then f inverse of v intersect A is non-empty, right? It has some point. We'll apply f to that point. What do you get? Well, f of that point is going to be in v, and it's going to be in f of A. Hence, by applying f, we have v intersect f of A is non-empty. So f of x equals y is in the closure of f of A by 79. Does that make sense? What? I don't know what that means. I don't know what the L means. Oh, wild. Oh, I thought it was an acronym. All right, well, living the dream right now. Cool. But notice, right, like, I basically did it every step, the only thing that I could really think to do, right? This is all just, like, using definitions, and you just kind of end up where you need to be. The next one is a lot less intuitive to me. So I want to try to set it up a little bit, right? So here I have know for any a subset of x that f of a bar is contained in f of a bar. And I want, if C is closed, then f inverse of C is closed, right? I want my preimage of closed to be closed. So, you know, there are a lot of different ways to think about being closed. You know, your complement is open, and stuff. But, like, here, thinking about what we have, stuff about closures, it's probably going to be useful to think of this being equal to its closure, right? That seems like the route that we should take. So probably use, or so maybe, so really we want that f inverse of C is equal to its closure. But we always have one direction here, right? So, I mean, this is always true. So this is what we need. And so bar, f inverse of C bar, its closure. Yeah, the bar is important. Otherwise, yeah. It looked like I was like underlining y is closed or something. Gotcha. Yeah, no. We want that it's equal to its closure. Right. And so this means that we would like to show if x, so again, this is still in the want stage. If x is in the closure, then x is in the preimage. But being in the preimage, right, means that f of x is in C. So really what I want to show, this is my last one, I swear. I'm just trying to break this down into like what I actually want to give direction, because otherwise this is just going to seem really non-intuitive. So I start with x over here, right? And I want f of x to be in C. So what I really want to show is that f of this closure is a subset of C. This is the key. Okay, why? Because this is very nice. This is exactly in my form f of a bar, right? So this kind of tells me maybe let A be f inverse of C, because I'm seeing f of something bar, right? Okay. So if I do that, then f of a bar being a subset of f of a bar implies that f of the closure of C is contained in the closure of f inverse, the preimage of C. Now, where do you know the preimage or the image of the preimage lies? We always have yeah, so it's going to be inside C. Right, because these are the things, the preimage is exactly the things that map to C, and then you map them. So they're going to be in C. So now we have f of the closure of the preimage is a subset of the closure of C. But C is closed, so this is equal to C. And that's exactly what I needed, right? I have exactly this is contained in C. And so if you just kind of backtrack there, right, then all that I used up here means that we get what we want. So, right, if x is in f inverse of C bar, then f of x is in C, so x is in the preimage of C. So the closure lies within the preimage. Thus, this guy is closed. That's actually a great gif. I miss Chris Farley. Funny dude. So again, I tried to make that more intuitive. I know that one's weird. That step always feels strange to me. I say always as if I've done it a lot. I've done it like 3 times in my life probably. But it always just feels a little bit strange. And that's why I think like doing this preamble and really trying to like suss it out and figure out like how the heck does this apply? Right? Because like you can mess around with this for like 2 hours and then finally figure it out, or you can really try to like from the start get at like how does what I am given apply, and then it kind of naturally leads you to the answer. If you just try to like get there randomly, it's going to take a long time unless you're like very lucky. Yeah. It's a weird one. 3 implies 4. Wait, yes. Yes. What is... Oh, there it is. Okay. So now we know that preimages of closed are closed. And we want for any x in X and V open neighborhood of f of x that there exists an open neighborhood U containing X such that f of U is contained in V. Alright, so again, there's only like one real sensible way of doing this. You have to figure out like what closed set makes sense, right? So you start with some x in X and let V be some open neighborhood of f of x. That's where we start. We want to find this open set. Well, we only know stuff about closed sets. What closed set would you like to consider here? I think there's only really one that makes a ton of sense. Okay, maybe there are two that make sense. You could take y, but like that's not going to really help us because that's not going to be specific to v at all, right? Like this should somehow rely on v. V is open. If you have an open set, how do you get a closed set? There you go, complement. Okay, so consider y minus v, which must be closed. Well, then f inverse of y minus v is closed. Preimages of closed are closed, right? So by assumption. And by 27, like I mentioned earlier, f inverse of y minus v, whoops, getting ahead of myself, is the preimage of y minus the preimage of v. What is the preimage of y? Well, that's just everything, right? And then I have this guy. Okay, well this is closed, right? So x minus f inverse of v is closed. So f inverse of v must be open. Moreover, we get what we want, right? This is my u. I want u such that f of u lies in v. Well, by definition of the preimage. Oh, sorry. Because it is this set, which is closed by assumption. Well, no, it's closed by our assumption that preimages of closed are closed. This guy is closed, so its preimage is closed by our assumption. Yeah. And so like the last step here is that f of f inverse of v is contained in v. So let our u be f inverse of v, and we are good. We get what we want. Ah, 4 implies 1. So the last one, we want to show f is continuous, right? And so here we know the thing above. So for any x in x, v containing f of x, that there exists a u such that x is in u and f of u is contained in v. Okay, and then we want f inverse of v is open for any v open in y. Right, we want preimages of open to be open. We're back to the start. So let v be open. What I'm going to do is I'm going to show that f inverse of v is a union of open sets. And we're going to use that theorem 12 because what this does, right, so we show f inverse of v is a union of open sets. Alternatively, I mean, this is basically showing that it's equal to its interior. We're just going to take the neighborhoods around every point inside it, right? So let x be an F inverse of V? Well, that means f of x is in V, right? So we have an open neighborhood of f of x. So there exists some u that depends on x here, such that f of ux lies inside V. Turning this into a statement about preimages, this just means that ux is contained in the preimage of V, right? Because all of the things in ux map under f to V. So all of the things in ux lie in the preimage of V. Well, what does that mean? This means f inverse of V is equal to the union over all of the x inside it of these ux's, right? Because all of the ux's lie inside. I've taken every point, and so I have inclusion both ways. And these are all open. And so this guy is open. And we're done. So yeah, that was the long proof. Questions? Thoughts? All right. Well, problem set is due on Saturday at 5. Correct. Yeah. 6? Yeah. Whenever it says it's due. Yeah, I think I did make it 6. Yeah. 6 it is. Cool. All right. Well, I'll be around for a bit, and I'll also be around this afternoon. I will not really be around this evening. I have a review session for Calc 2 for their exam, and I have to write said exam. So, yeah, if you have questions on that stuff, during the day is much better, or just tomorrow. But during the day today is also fine. Don't wait to start too long. Alrighty. Have a delightful day. I hope to talk to you guys later.